Welcome to this last lecture on the vector semantics. I have already shared the slides, but I could not record my audios for these slides. So, here it is. So, objective here is to discuss the sort and dense vector representation of words. So, in the initial part of the vector semantics, we have looked into some examples of obtaining the long and sparse vector representation. But now we will focus on the obtaining the sort and dense vector representation, and in that particular thing we are going to first look into the latent semantic analysis or latent semantic indexing, which is essentially is a singular value decomposition on the co-occurrence matrix. And then we are going to discuss the global vectors, or in short the GLO. While discussing this LSA, I will just briefly recap of some of the important matrix decomposition algorithms. So let's look into them. Although we are not going to directly use this for the decomposition of square matrix in this particular lecture, but nevertheless this is an important decomposition algorithm, so I just wanted to recap. So given any square matrix, we can convert them into product of the three spatial matrices, in fact under certain conditions. So if S is a square real valued matrix, and if it has a m linearly independent eigenvectors, so S is a m cross m matrix, and if you have m linearly independent eigenvectors, then we have an eigen decomposition. So this is actually, we can call it matrix diagonalization theorem or the eigen decomposition of matrices. So S can be written in the form of product of these matrices, where U is the columns of U are basically the eigenvectors of S, and this big lambda is a diagonal matrix where diagonal entries are the eigenvalues of S in decreasing order. And if the eigenvalues are distinct, then we have this decomposition is unique. The symmetric diagonalization theorem says that if on top of S being a square matrix, if it is also a symmetric and real valued m cross m matrix with m linearly independent eigenvectors, then you have a symmetric diagonal decomposition, where now the Q matrix, which is again the columns of Q are the eigenvectors, but they are now the orthogonal eigenvectors of S. So basically S being a symmetric matrix give rise to the other properties for the eigenvectors, that they are the orthogonal eigenvectors, and this lambda is again the same as the last the eigenvalue decomposition, or the matrix diagonalization theorem, that these are the eigenvalues, and then you put into them into a decreasing order. And there is essential properties that the Q transpose is basically the Q inverse. So these two matrices, although we are not going to use, but these are the important diagonalization theorem, has multiple applications in machine learning. Now what we are interested in is this SVD theorem, which is basically the decomposition of a rectangular matrix. So if you remember that our term context matrix or the term document matrix often is in the they are rectangular matrix. So let R be the rank of the m cross n matrix C. So by rank we mean that the number of linearly independent rows or columns in the matrix C. The singular value decomposition of C is of the form. This can be obtained as a U sigma V transpose, where the sigma are basically the eigenvalues of the where we have first this lambda i's, lambda 1 to lambda r, as r is the rank of this matrix, so we have r eigenvalues, and that they are the eigenvalues of the C transpose matrix or the C transpose C. So it's basically for both the matrices the same eigenvalues are obtained, and then you take the square root of each of these eigenvalues, and that is what is called the singular values, and then put into a decreasing order, and rest all other entries will become 0, and that is what is this big sigma matrix. And U and V transpose is basically the corresponding so U is the columns of U is basically the eigenvectors of C transpose, and V is basically the eigenvectors of the C transpose C. So this is what the singular value decomposition means, and why it is important we will see in the subsequent slides. So what our objective here is that, see that what we have given is a very long and sparse vector representation, and we want to obtain a short and dense vector representation. So our objective is that given in this M cross N matrix C, we want to obtain M cross N matrix Ck of at most rank at most rank K. So that so first let's look into this, what do we mean by the low rank approximation, and then we will discuss that how this is useful in case of our objective, or how it is helpful to achieve our objective to obtain a short and dense vector representation. So in the low rank approximation, given a matrix M cross N C matrix, our objective is to obtain a matrix of a lower rank. This rank K is much smaller than the rank of matrix given matrix C. So for example, if we are considering this term document matrix where tens and thousands of the words are there, and then the documents are also in hundreds of the thousands and so on, or in the millions. So the rank of such matrices would be very high, and we don't want to really look into those high rank matrices. We want to obtain a low rank matrix of maybe few hundreds or so. So the K is very, very small, but we want to find that matrix which so we want to obtain a matrix Ck of rank K in such a way that it should minimize the Frobenius norm of the matrix difference C minus Ck. So what do we mean by Frobenius norms? It's basically that you just look into the matrix difference, and then you look into each entries of those matrix differences, and then you just take the square and then sum over all the rows and the columns. So or basically all the entries. So that's what the Frobenius norm is, and that's what we want to minimize. So if R is the rank of the matrix C, then if we look for the Ck, and so this is a small k, then Cr, so as per this notation here, the Cr will be equal to C, and then our Frobenius norm is 0. So as I said that if K is far smaller than N, then we refer to Ck as a low rank approximation of the matrix C. So that definition is clear, hopefully. So now how we can obtain a low rank matrix, low rank approximation using singular value decomposition. So what we do is, we given a matrix C, we construct its SVD in the form U sigma V transpose. From sigma we derive the matrix sigma K. How do we do that? What we do is that we replace the R minus K, the smallest singular values. So you remember that the singular values sigma i's are basically the square root of the lambda i's. Lambda i's are the eigenvalues of CC transpose. So and then we put them into the decreasing order. So sigma 1 is greater equal sigma 2 2, and then so on. So by looking at that, so what we do is that the smallest R minus K, the sigma values, we are going to put them into value 0, because after, let's say, sigma R plus 1 onwards, anyway everything is 0. So what we do is that we R minus K, we are making them 0. So this everything becomes 0 now, and then we compute the matrix CK by considering this modified diagonal matrix sigma K, where now only the K entries are basically non-zero. R minus K entries has been made 0, and rest other entries are anyway 0. So the CK has this CK matrix is the rank, its rank is K, and that is what is the rank K approximation to C. Remember, the CK matrix is also an M cross N matrix. So now the question is, what is the guarantee that this step is actually giving that what we want? I mean, this is our what the low rank approximation matrix says. Why this will work? So this will work because Descartes and Young theorem says that if you want to obtain the matrix Z and of a rank K, and you want to sort of minimize the Frobenius norm of this matrix difference, then the CK matrix as obtained by this, as whatever described as steps here, the CK matrix, this difference is basically sigma K plus 1. And if you see that, as we know that this sigma i's are basically in a decreasing order, so that sort of says that this is a sort of small quantity, and with this theorem that guarantees that yes, this is what we are going to obtain. And if you see that if K is equal to R, then this approximation gives us sigma R plus 1, and that is 0. So that means that this is the CR is basically the same matrix as the C. So with this low rank approximation, now we know that we can use this SVD to obtain a low rank approximation matrix CK. Now try to understand that. Now let's try to understand that how we can use uh, you know this whatever we have discussed as an the latent semantic indexing and how it can give us the document representation or the word vector representation in terms of let's say the sort and the dense vector representation. So let's assume that this is what the C original matrix, which is the term document matrix, and now we have this U, sigma, and V transpose. So that we have done this SVD of this matrix, and which gives rise to these three matrices U, sigma, V transpose. Then let's assume that we want to look into the k equal to 2. Okay, so that means only the two entries here we will let it be non-zero, and rest other we are going to make it as a 0. So that's what we have done here. The sigma 2 is only these two entries are non-zero, rest everything becomes 0. So now the C2 is now we have obtained by looking at sigma 2 V transpose. So that's what gives us the C2, and this is what our vectors representation, this is what the C2 matrix, and you can see that now this gives us in the transformed space, of course, the representation of the documents. So now since all of these things are 0, we don't really have to consider them, and only these two vectors are basically. So this is what the transformed space gives us the document representation. Now so for example, in terms of, this is an example related to the information retrieval, that if you have any query vector, so and then you want to find a similarity of that query with respect to the document. So originally the Q would be represented again in terms of these vocabulary set. Okay, so this would be again any of this your query is basically in the dimension of the the V dimensional representation. But here it's actually now you want to look for the representation which is much smaller. So here it's a 2-dimensional and here it's a 5-dimensional. So now this Q needs to transform into this vector space, and that can be transformed. So this is again the application of the linear algebra where you have to transform. So this is a kind of an example of linear transformation where you have a vector in one vector space and you want to transform into another vector space. So how we can do that? So although I have not really derived it, so I am directly giving you the formula. So this query vector Q is now represented into this transformed space by multiplying this Q with these vectors. So that gives rise to the query vector in the transformed space, and then now you can look into you can compare this query with this document or this document or this document. So each of these documents you can now directly compare. In fact, this SVD decomposition is actually, you can do it in an incremental way, in the sense that if the new document comes, now that document can again be easily transformed into this the new vector space by again using the same formula. Okay, so similarly you have your similar things can be also done with respect to the words if you want to obtain a representation of words in terms of the term document matrix, using the term document matrix. So that's about this the LSA to how to obtain a dense and the sort vector representation, and next we will discuss the global vector